Chapter 5, Lesson 2, Sequences. Vocabulary Startup. A sequence is an ordered list of numbers. Each number in a sequence is called a term. In an arithmetic sequence, each term is found by adding the same number to the previous term. We're going to complete the graphic organizer below for an arithmetic sequences. So this word that I'm circling is pronounced arithmetic, not arithmetic. So practice saying arithmetic. Say it one more time. Arithmetic. So for numbers, we're going to continue each sequence. 1, 3, 5, 7. Next one's going to be 9 because those are going by odd numbers. The next sequence is 1 to 1.5 to 2 to 2.5, 3, and lastly 3.5. Now if you notice, there is a ... after both these sequences. That is implying that this sequence is continuing. It's not terminating. So words. Describe each sequence. You're going to add 2 to the previous term. That is for the first one. Again, adding 2 to the previous term. Then for the second sequence, we are going to add 5/10 to the previous term. Horseback riding. The number of students who went on each horseback riding trip is shown. Do the numbers represent the terms of an arithmetic sequence and explain? So if we look at our trip, the first trip, second, third, fourth, and fifth, the number of students goes from 15 to 16, so that was adding 1, 16 to 18, that's adding 2, 18 to 21 is adding 3, 21 to 25 is adding 4. So to answer the question, do the numbers represent the terms of an arithmetic sequence? This is going to be a no. The same number is not added to the previous term. The numbers increase by 1, 2, 3, and 4. If it was an arithmetic sequence, it would be increasing by the same amount every time. Perhaps 1 every time, or 2, so on and so forth. So let's continue and go to the next page. We are going to describe and extend our sequences. So in an arithmetic sequence, the terms can be whole numbers, fractions, or decimals. So let's look at some examples. Number 1, we're going to describe the relationship between the terms in the arithmetic sequence 8, 13, 18, 23. So I'm going to show my work to the left. 8, 13, 18, 23. To get from 8 to 13, I add 5. To get from 13 to 18, I add 5. 18 to 23, I add 5. ... So I could continue with this pattern. So it says, then write the next 3 terms in the sequence. So that means I'm going to take 23 and I'm going to add 5, which gives me 28. I'm going to take 28 and I'm going to add 5. That gives me 33. And then I'm going to take 33 and I'm going to add 5, which gives me 38. So the next 3 numbers in my sequence are 28, 33, and 38. Number 2, we're going to describe the relationship between the terms in this arithmetic sequence. There are 4/10, 6/10, 8/10, 1 and 0/10. Then we're going to write the next three terms in the sequence. This is number 2. So I have 4/10, 6/10, 8/10, 1 and 0/10. So to get from 4/10 to 6/10, I'm adding a 2/10. 6/10 to 8/10, I'm adding a 2/10. 8/10 to 1 and 0/10, I'm adding 2/10. Oh, not 2. I'm adding 2/10. So in order to find the next 3 in this sequence, I'm going to start with my 1 and 0/10, and I'm going to add 2/10. So that gives me 1 and 2/10. Then I'm going to add another 2/10. That gives me 1 and 4/10. And once again, add 2/10 gives me 1 and 6/10. So my next 3 terms are 1 and 2/10, 1 and 4/10, 1 and 6/10. Let's see how you guys are understanding this. So we're going to take letter A, 0, 13, 26, 39. 0, 13, 26, 39, dot, dot, dot. So to get from 0 to 13, I add 13. 13 to 26, I add 13. 26 to 39, I add 13. So to answer the first part, describe the relationship. Add 13 to the previous term. So to continue with that, if I add 13 to 39, that's going to give me 52. Add 13 gives me 65. Add 13 gives me 78. So that gives me 52, 65, and 78 for my next 3 terms. And it would continue from there. Letter B, 4, 7, 10, 13. 4, 7, 10, 13. To get from 4 to 7, I add 3. 7 to 10, I add 3. 10 to 13, I add 3. And to continue, 13 plus 3 is 16. Oops. Plus 3 is 19. Plus an additional 3 gives me 22, not 21. Gives me 22. So that was answering the second part. The first part was to describe the relationship. You add 3 to the previous term. All right, let's look at letter C. We're at 1 and 0/10, then 1 and 3/10, so I'm adding 3/10. I add another 3/10 to get from 1 and 3/10 to 1 and 6/10. And then 1 and 6/10 to 1 and 9/10, I'm adding another 3/10. So I want to add another 3/10. It's going to give me 2 and 2/10 plus another 3/10 gives me 2 and 5/10. And lastly, 2 and 8/10. Once again, I am answering the second part. So to describe the relationship, you add 3/10 to the previous term. All right, let's look at letter D. 2 and 5/10 to 3 and 0/10, you're adding 5/10. Adding another 5/10, and you're adding another 5/10. So continue with that pattern, that becomes 4 and 5/10, 5 and 0/10, 5 and 5/10. So those are going to be my next 3 terms. Then to describe the pattern, you add 5/10 to the previous term. As a reminder, term is just referring to the previous number. So now we're going to write an algebraic expression. So in a sequence, each term has a specific position within the sequence. So let's consider the sequence 2, 4, 6, 8, so on and so forth. The first position is number 2. The second position is number 4. The third position is number 6. And lastly, the fourth position is number 8. So notice that as the position numbers increases by 1, the value of the term increases by 2. So as a reminder, first position, second position, third position, fourth position. So when they're saying the position number increases by 1, it's referring to the position 1, 2, 3, and 4. But the value of the term increases by 2. So 2 to 4, 4 to 6, 6 to 8, we're adding 2 each time. So if you notice, they broke this in, or I'm sorry, they put this into a table of values. So they broke it down to where you have the position in the first column. So that's 1, 2, 3, 4. Then they have the value of the term in the last column, 2, 4, 6, 8. Now in the middle column, that is the operation. So that's meaning 1 times 2 equals 2. 2 times 2 equals 4. 3 times 2 equals 6. 4 times 2 equals 8. So this means that we are multiplying by 2 each time. So you can also write an algebraic expression to represent the relationship between any term in a sequence and its position in the sequence. In this case, we're going to have n represent the position in the sequence. So that's this, we'll just say down here, n. Adding a extra row into my table. So my nth position times 2 is going to be 2n. So the value of the term is 2n. I'm just extending my... So in this case, if n is the position in the sequence, the value of the term is 2n. So let's try this example. The greeting cards that Meredith makes are sold in boxes at a gift store. The first week, the store sold 5 boxes. Each week, the store sells 5 more boxes. The pattern continues. What algebraic expression can be used to find the total number of boxes sold at the end of the 100th week? What is the total? Well, each term is 5 times its position. So the expression is 5 times n. So if you notice, it says n times 5, but we always want to put our number in front of our variable. So the number is called the coefficient. The coefficient goes in front of our variable. So we want to write the expression. Now, in order to find the cost at the end of the 100th week, and I apologize. Yep, cut off a little bit, but that's okay. We are going to replace n with 100. So instead of it being 5n, it's going to be 5 times 100. 5 times 100 equals 500. So at the end, oop, at the end of 100 weeks, 500 boxes will have been sold. So let's try the next problem on the next page. So let's see if you got it. If the pattern continues, what algebraic expression can be used to find the number of circles used in any figure? How many circles will be in the 50th figure? Well, personally, I'm going to make a table just like in my previous problem. So I'm going to take my position, which is going to be 1, 2, 3, and then we'll say the nth position. Bear with me. So here's my position. Then I have my operation. And then lastly, I have my value of term. My first position's value is 3. My second position's value is 6. My third position's value is 9. So this is referring to 1 times 3, which equals 3. No, I'm sorry. I'll just leave it as 1 times 3. Then we have 2 times 3, 3 times 3, and then we'll have n times 3. Well, n times 3 becomes 3n, because again, the number goes out in front because it's the coefficient. So here's my algebraic expression, 3n. And in order to find the 50th term, I am going to replace n with 50. So this is going to be 3 times 50. So instead of 3n, it's 3 times 50, which equals 150. So there will be 150 circles inside the 50th figure. Great job. Go forth and do some practice.